In today's class, we shall have a look at Shannon's theorem. Now, we have already seen Shannon's first fundamental theorem. Now, we shall have a look at Shannon's theorem for channel coding, that is also called as Shannon's second fundamental theorem. Now, the Shannon's theorem is concerned with the rate of the transmission of information over a communication channel. Now, this is the theorem. Let us see what it says. The Shannon theorem says that it is possible to devise a means whereby any communication system will transmit information with an arbitrarily small probability of error, provided that the information rate is less than or equal to a rate C, which is channel capacity. So, it is concerned with the rate of transmission of information. Now, we have already seen what is mutual information and we have also seen what is the meaning of channel capacity previously. Now, with respect to a communication system, in a communication system there will be a transmitter, a receiver and a communication channel. Now, this channel can be a wired medium, it can be a wireless medium. So, there are different channels which we have seen previously. Now, this particular theorem is to do with the transmission of information. So, from the transmitter to the receiver, we are going to send some information and that would be sent over the communication channel. Now, what we have seen previously is, first we have seen something called as information rate. And what is information rate? Information rate, capital R, is nothing but R into H. So the R into H is nothing but the entropy, and R is nothing but the rate, that is your rate of the data, and that is the bit rate you can say, or rate of the source you can say. So information rate is depending upon the rate of the source and the entropy of the source. Now, we have already seen the statement. What it says is that as long as this particular R, which we have seen, as long as R is less than C. Now, R is less than or equal to C. What is this R? This is nothing but the information rate, and C is nothing but the channel capacity. So, as long as R is less than or equal to C, it guarantees that it is possible to have a communication system which will transmit the information with a very small probability of error. So what I am saying is that it is possible to transmit information over this particular communication channel. Now, this is what Shannon, who is also called as the father of information theory, he proposed this particular theorem, and he said that if R is less than or equal to C, it is possible for us to have a communication system which will transmit the data or transmit the information with a very small probability of error. But he just proposed this theorem and he did not show how it would be possible. We know that it will be possible from his theorem that it will be possible to transmit the information if at all R is less than or equal to C. But how the communication system will achieve this, that was not guaranteed by this particular Shannon's theorem. But yet this theorem is very important theorem, and because of this later on the researchers went into research and they developed different techniques such that it is possible to transmit information from the transmitter to the receiver with a very small probability of error. So that is what was predicted by Shannon, and he proposed it as a theorem, and then it has been proved later on by people, other researchers who have developed so many techniques and have shown that it is possible. Now, so once again I would like to go through this theorem. It says that it is possible to devise a means whereby a communication system will transmit information with an arbitrarily small probability of error, provided that R is less than or equal to C, and where C is nothing but channel capacity. This is the exact statement of Shannon's theorem. Given a source of m equally likely messages such that m is much greater than 1, which is generating information at the rate r. So what we have two things. One is we have a source which is generating m equally likely messages. So I have a source which is generating m equally likely messages. Why equally likely messages? Because whenever m equally likely messages, your entropy would be maximum in that particular case. So entropy would be maximum, as in your information rate also would be maximum, because if r is nothing but small r into h, if h is maximum, r also will be maximum. So there is a source which is generating m equally likely messages at the rate r. So the rate of the source is capital R. And there is a channel here, there is the channel through which the data has to be transmitted, and the channel capacity is C. So if R is less than or equal to C, there exists a coding technique such that the output of the source may be transmitted over the channel with a probability of error of receiving the message very small. So the error of probability will be very small. So that means that if at all I send a message x1, x1 will be received at the receiver. If at all I send a message x2, x2 will be received. So the probability of receiving a wrong message is very less. So this indicates that for r less than or equal to C, error-free transmission is possible in the presence of noise. Now please remember that, what does it mean? I have not told you that there is no noise in the system. In the moment we consider a channel, there will definitely be noise, and I have not said that there will be no noise in the system. But in spite of there being noise, it is possible to have an error-free transmission. Now in this particular communication system which is included, I have shown the source and the channel, and there is a receiver which is there. Now in this particular channel you would be transmitting the data. Now what I am saying is that it is, besides transmitting some data, there will be some noise also which will be present in the channel, because in the noise, the channel, there will be noise. Now I am not saying that there is no noise. Whenever there is no noise, then supposing if at all I am transmitting 0, 1, 0, 1, 0, then at the receiver, because there is no noise, I would be getting 0, 1, 0, 1, 0. Now, I am not saying that there will not be distortion. There can be distortion also in the channel. Distortion and noise are two different things. There could be some distortion in the channel such that, such that the data is not being, you cannot reconstruct the data back again. But what I am saying in this case is that, supposing that there is no noise and no distortion through the channel, then whatever data is being transmitted, that would be received, right? But supposing if there is noise, then what will happen is that if there is noise, also it is possible to get the data back. Supposing if you are transmitting this particular data and there is noise, so along with the noise your data may not be like this, it would be something else only. But it is possible to remove the noise or do something such that I will get the same data back. So, but provided, what should be the condition? The condition should be that the information rate R should be less than or equal to C, that is the channel capacity. It is as simple as this. What is the capacity? Now capacity of a bus, supposing that I take an example of a bus. Okay, now a bus has to go from Margao to Panjim. Now if it is a Kadamba bus, KTC bus, Kadamba bus, and it is your shuttle service. Now shuttle service has got a maximum strength that it can take say 30 passengers. So if at all the number of passengers are 29, yes, 29 is less than 30, That means this Katamba bus will take them from Margao to Panjim. If at all the passengers are 35, which is greater than 30, it will not take the 35 passengers, but what will happen is that it will take only 30 passengers. So, that is what is the capacity of bus. So, anytime the actual situation, whatever you are transmitting cannot be more than the capacity, like the passengers who have to go through the bus cannot be more than the capacity of that particular bus. Similarly, the information which you are transmitting, the rate of information which you are transmitting cannot be more than the channel capacity. If at all I tell you that this particular channel capacity is this much, I cannot have more information than that. The rate of information cannot be more. So supposing that I say that the channel capacity is 1 megahertz. I cannot send a signal which is 2 megahertz. Okay? Or rather I cannot send a signal which is having an information rate of 2 Mbps, because it is greater than the channel capacity. That is what we will be studying here. So the channel capacity is also going to be represented in bits only. Although I have just given you a rough example that channel capacity is 1 megahertz, but it won't be 1 megahertz, it will be 1 megabits per second, because we are in the digital domain. So it will be represented as 1 megabits per second. So a 1 megabits per second channel cannot have information rate 2 megabits per second. Okay? So it will not ensure. It is not saying that it cannot transmit, but it is saying that error-free transmission is not possible. You may be able to transmit, but there will be a lot of errors. That is what is predicted by Shannon's theorem. Fine. Now there is a negative statement of Shannon. Now what does this negative statement of Shannon's theorem tells us? Same thing. Given a source of m equally likely messages with m much greater than 1, which is generating information at the rate r, and given the channel capacity c. Now the first 2 points are the same, that's why I have separated them. It is one theorem only, but it says that r is greater than c. I just took an example. I took r as 2 Mbps and c as 1 Mbps. What will happen there? Okay, in this case the probability of error is very close to 1 for every possible set of m transmitted signals. What does it mean? All the codes which you are transmitting will have some probability of error, which increases as the rate increases. So if r is greater than c, then there will be some probability of error. There will be errors taking place, and as r increases, the probability of error also would increase. So the information, final conclusion is that information cannot be transmitted at the rate beyond the channel capacity. So I cannot have r greater than c. This is not possible, or we have to avoid this particular situation. Otherwise, no information will be transmitted. Now, we have seen previously that there will be noise in a system, and I have told you that in a system, in the channel, there will be source, and in the channel there will be some noise which would be present, and then there is a receiver. Okay. Now, what type of noise is usually considered in a communication system? In a communication system, mostly this noise, whatever we are going to consider, it is additive white Gaussian noise. I would just like to explain to you what is the meaning of additive white Gaussian noise. Now it is a model, it is a basic noise model used in information theory to mimic the effect of many random processes occurring in nature. So there are different processes, random processes which will be occurring in the nature, and these are all going to be modeled with the help of a particular type of a noise that is called as AWGN, that is additive white Gaussian noise. Now, that is any noise in general, whenever we consider, we would be considering white Gaussian noise. Now, why the name is AWGN, why it is additive white Gaussian noise, we shall have a look at it. So why it is additive? First, because it is added to the any noise intrinsic into the system. Now, very important concept is there is internal noise and there is external noise. Now, this is your receiver. Within this receiver, there will be already some components which will be causing noise, and that would be the intrinsic noise. Okay, and this noise which is coming from the external environment. So this is AWGN noise, and this noise is added, okay, it is added to the signal and to the noise which is already present within the receiver. That is the reason it is called as additive noise. Now next is the term white. Why is this noise called as white noise? Does it have a color? Does noise have a color? Why it is called as white? Now it is called as white because of the fact that it contains all frequency components in equal proportion. Now simple example I would like to give you is of white light. Now white light which is there, white light, if at all you know, it consists of all different colors. Yes or no? White light consists of all different colors, and when all different colors are added together, it forms white light. So that is the reason all different colors would be forming white light. So whenever all colors are mixed with equal proportion, it would give you white light. Same thing here. This particular noise is present at all frequencies, and that is the reason it is called as white noise. So it has uniform power across the frequency band for a system. It is not that at a particular frequency it is more, at a particular other frequency it is less. There is nothing like that. The amplitude of the noise is uniform at all the frequencies. So the mass spectral density of white noise is given by Sn of f, which is eta by 2. Now what does it mean? That is the mass spectral density of white noise is independent of frequency. Does it depend upon the frequency? The equation itself tells us that there is no frequency term. There is no frequency term here in this particular equation. So it doesn't depend upon the frequency. So that is the reason we say that it is independent of frequency, and it is a constant value, that is eta by 2. It is a constant value. So eta is a constant. So what you can say is that the PDF is uniform over entire range of frequencies, including positive and negative. So if at all I would like to draw the power spectral density of white Gaussian noise, power spectral density, it is the plot of power, signal power, or in this case it would be the noise power with respect to the frequency as a function of frequency. And what I will get this graph is, this graph would be flat, that is a constant, and this value is nothing but eta by 2. So this means that this particular white Gaussian noise is constant at all frequencies, positive as well as negative. Now we shall go to the next term, that is Gaussian. Why it is called as Gaussian? It is called as Gaussian noise because it has got Gaussian or normal distribution in a time domain with an average mean value of 0. So if at all I have to plot the voltage waveform of noise, so this is noise with respect to time in the time domain. So how is noise? It is having a very random nature like this. Okay, you all would have seen this. This is somewhat like this would be the noise. I am just drawing some noise randomly. Now what you can see here, most of the time the value of noise is 0. Now noise is in the positive half as well as the negative half, right? So if at all I can find something called as the probability distribution function with respect to the volts, and I can plot this probability distribution function and see what we get. So if we take the PDF of noise, what we would get is that we would be getting a bell-shaped curve. So we would be getting a bell-shaped curve which is symmetrical on both the sides of the F, the V axis. So why you get this is that if at all you look at this time domain behavior of noise. Now most of the times the noise is located around 0 volts, right? It is not somewhere having a very high amplitude. No, it is somewhere within this particular range. It is somewhere within this particular range. But very rarely it can go outside this range, positive as well as negative. So most of the times the noise is around 0. So now see here the voltage axis. Now this is the voltage axis here. This voltage axis, which is the y-axis here, is drawn as the x-axis here. So what you can see that the noise is mostly at 0. And what is the 0 here? Here. This 0 which is on the y-axis here becomes the 0 on the x-axis here. And what you can see is that this noise is mostly fluctuating somewhere here. So when I draw the probability distribution function, it is mostly that the noise would be here. Okay, and mostly, and that is the reason at 0 it has the highest value, that is the probability is highest. Okay, this is PDF meaning probability distribution function. So the probability of noise is highest here at 0. That means most of the times the noise would be 0, but sometimes noise can be positive. As you can see here, noise can be positive. So this is your positive side of the noise, and sometimes the noise can be negative here, the way it is shown here. Sometimes the noise can be negative. So here is the negative side of the noise. So if at all I plot the probability distribution function of noise, it is having the shape of a bell. This is the bell-shaped curve, and this bell-shaped curve, whatever we get, we call it as Gaussian distribution or normal distribution. So what you can see is that why the mean of this particular, the average is 0. Why? Because it is there on the positive as well as negative, and it is symmetrical. So that is the reason it is not exactly symmetrical, but it is assumed to be symmetrical. So this Gaussian PDF, what we get here, what we have drawn here, this would be symmetrical on both the side of 0. Okay, so that is the reason it is called as, draw again, it is symmetrical. So that is the reason the mean value is 0. Now sometimes if at all the mean is not 0, then I can draw it like this. 0 will be here and the mean will be here, okay, of a Gaussian distribution. But in case of noise, most of the times the noise is having a Gaussian distribution. The mean will be 0, and what we get here would be sigma, that is a standard deviation, or sigma square is nothing but variance. So this is sigma, that is standard deviation. Now what is the equation for the Gaussian noise? So what you should know here is that the Gaussian noise is a bell-shaped curve, and it has got a PDF which is going to be Gaussian PDF. Now the Gaussian noise PDF is bell-shaped, and the peak value is centered around 0 value, and that is the reason your mean or the average value of this is 0. And as you see that as the value of the volts increases on both the sides, it may be on the positive side or on the negative side, this side or this side, the voltage, the noise voltage goes on reducing. Now what is the equation for the Gaussian PDF? Gaussian distribution, probability distribution function is given by f of v is equal to 1 upon root 2 by sigma e raised to minus v square upon 2 sigma square, where what is v? V is nothing but, I can write v minus mu, but since mu is equal to 0, mean is equal to 0, it is not being written. So sigma is nothing but standard deviation, and sigma square is nothing but variance. So now having seen this, we shall go to the next theorem, that is called as Shannon-Hartley's theorem, and it is very important because with the help of Shannon's theorem we knew nothing. Okay, it was something which is true, but there was no means by which you could tell that okay, you go in this particular direction and there would be error-free transmission. No, there was no guidance which was given, but later on there was a particular theorem which was in addition to Shannon. So it was given by Hartley also. So it is called as Shannon-Hartley's theorem, which is very important along with your Shannon's theorem. So it is a theorem which is complementary to the Shannon's theorem, and it is applied when the noise is Gaussian. Now previously I have explained to you what is Shannon's theorem. Then I have explained to you what is Gaussian. So I have explained to you what is Shannon's theorem, and then I had explained to you what is Gaussian noise. Now while I was telling you about Shannon's theorem, I did not tell you anything about noise, right? We spoke in general about a communication system, but now when we assume that the noise in a particular channel is Gaussian random noise, Gaussian or your AWGN, additive white Gaussian noise is present in a communication channel, and then you are applying the Shannon's theorem, then we get this Shannon-Hartley's theorem, which is very specific one. Okay, and it is complementing, it is giving you more information than the Shannon's theorem. So it is a complementary theorem to the Shannon's theorem. So what it says, let us see what this particular theorem says. It says that the channel capacity of wide band limited Gaussian channel is this. So whenever we have a wide, that is AWGN noise, the channel capacity is given by this equation. Previously we did not know what is C. We knew what is R. R is the information rate, but nothing was known about what is C. What is this channel capacity? So here we have got an equation for channel capacity, and where C is nothing but B log to the base 2, 1 plus S by n bits per second. But what is B? B is the channel bandwidth. What is S? Signal power. And N is nothing but the total noise within the bandwidth. Now please note that N is nothing but eta into B, with eta by 2 is nothing but the two-sided power spectral density. So now please note that you know how we get N is equal to eta into B. Now we saw that the bandwidth, the noise power spectral density is flat, and the value of it is eta into 2. Eta by 2. Now supposing that here the bandwidth is B. Now what happens is that if at all the bandwidth of the signal is B, usually what we have is that say bandwidth is B here. But we consider the positive side as well as the negative side. So the bandwidth which we consider would be twice B. And how much will be the noise present in this bandwidth? Noise present in this bandwidth would be this. So if at all I take the integration over this particular area, or this becomes a rectangle, so sides, this side is 2B and this value is eta by 2. So if at all I want to find the noise in a channel whose bandwidth is B, then that would be twice B into eta by 2. So 2 and 2 will get cancelled. Noise in that particular bandwidth would be eta into B. That is the reason we have got a noise as eta into B. So where eta by 2 is the two-sided power spectral density. Okay, so when we take bandwidth is, see, we have considered eta by 2 for two-sided, both the sides, that is positive frequencies as well as negative frequencies. So the bandwidth also will be for positive frequency as well as negative frequency, so it becomes twice B, and then it is multiplied by eta by 2, so 2 and 2 will get cancelled. So this is what we get. So now the Shannon-Hartley's theorem, what does it tell us? It tells us what is the equation of C, and the same thing what was told previously by the Shannon's theorem. So additional information is it tells what is the capacity. Now, what is the importance of the Shannon-Hartley theorem is that, see now, why we have considered only AWGN noise and why we have demonstrated this for only AWGN noise, because see what happens is that channels encountered in physical streams are at least approximately Gaussian. So most of the channels which are there in communication system, their behavior is almost like a Gaussian channel. That is, what I am telling is that how they will affect the noise. The noise in the channels will be most of the times, Gaussian noise. Therefore, the channels are Gaussian channels. If not 100%, then at least approximately it is a Gaussian channel. And whatever results are obtained for the Gaussian channel, it would provide a lower bound on the performance of the system operating over a non-Gaussian channel. Say supposing that, if at all we say that, there is a topper in the class, and if at all I asked a problem in the class, if at all the topper cannot solve the problem, I will say that nobody else can solve this problem. Okay, so it is somewhat like this. So, or in other words, I can say that I give a problem to a weak student. Okay, and if at all a weak student is able to solve this problem, I say that all the students will be able to solve the problem. So this is somewhat like whatever is true for Gaussian channel. So whatever result is obtained for the Gaussian channel will set like a lower bound. Meaning lower bound meaning, now if at all I see the topper, meaning it would be like the upper bound. If at all I see this weak student, it will be like a lower bound. So I am setting a lower bound, meaning if at all, what should be the easiest question which I should ask in the exam is what a weak student should be able to solve. Okay, and what should be the toughest problem I should ask in the exam is what a topper should be able to solve. So in this way I can set a lower bound and an upper bound. So same way here, Gaussian channel will set like a lower bound. So if at all the theorem works for a Gaussian channel, definitely it will work for the other channel. So that is the reason we have taken the Gaussian channel and then done this particular analysis. Is that clear?